So today I'm going to learn C, and I don't know really what I'm gonna do. Obviously, I already watched a bunch of things about C and C++ and assembly, but I never coded anything on these languages. So I think I'm just gonna use ChatGPT, and I think the first thing that I'm gonna do is write down on the file the next steps. I think I'm also gonna show what I did. Uh, at what point I stopped in the other project, but I managed to do everything that I want to do for now for the visualization. So I fixed the arrows and created the nodes. Yeah, and then I realized that I was putting the edges position in the wrong way, and that's why it was overlapping with the node. But I was also searching how to put the edge behind the other objects, but it's very hard to do, so I think I'm not gonna do it because it's not just a detail, and the way that it is now is much better, so I think it's good enough. But the first thing that I wanna learn is how to print statements. I think I need to figure out something to learn, like it's a project that I can do to learn. See, and I think I'm gonna try to build the compiler. It's not really a compiler, but the parser and lexer in C, because I already have the code from the other project, and because I think it might be better to, like, later on if I want to implement in more languages, I think that C is gonna be faster and it's gonna allow me to have like more. It's gonna be better for creating for multiple different languages, but maybe I'm wrong, so I might change this in the future. But I think it's worth learning anyway. So I think I'm gonna create a file here, and then I'm just gonna write down the steps. It's much better to do it. To do things with the steps. So otherwise it gets like too confusing, and I start thinking about a bunch of different stuff. So I think the first thing that I need to learn is what is the best way. And I think what I'm gonna do is just put everything on ChatGPT and then try to follow the steps and clarify. But the first thing I think is what is the best way to run C. I want to use VS Code if possible, because I don't like the Visual Studio from previous times that I tried to use. It's a lot worse than VS Code, so I prefer to do it on VS Code. C on VS Code. And I think I want to understand, because on other languages in Python and JavaScript, mainly what I do is just code and then I put a bunch of print statements or console logs everywhere to understand what is going on. But I don't know. I think that these other languages, like, because both JavaScript and Python are interpreted languages, so I think that these other languages are different because you create the binary first. Maybe it's similar to Rust, and I did some Rust, so but I want to think about, so what is the best thing? Is it better to create a project from scratch or try to study the other one and then try to incorporate? Maybe I should try to create a simple version of what I'm trying to do. I think that's probably the best idea, and then I can look at the other code if I get stuck. So maybe better match some string. Or I should try to create like from the beginning already. And I think I'm gonna look at this code here. I'm also looking at other videos and libraries on other languages on how to build this stuff. So a better match and try to create simple Maxer. So I'm just gonna start with this and I'm gonna use ChatGPT to see if I can figure out, and then if I can't, obviously I'm gonna search online on search engines. But I don't expect to get very far today. It's just gonna be to get myself familiar with the things. But I managed to do this stuff here last. Oh, I forgot to increase the size icon. Just remember this now. So maybe I'll do this before. I think I can't increase on here directly, so I'm gonna have to create another class, I think. Maybe I'll just increase a little. I'll do this. Oh, I already have a font size there. I'll do this off stream later. I just wanted to show before I start working on the other stuff. And it was easier than I thought it would be. This thing is buggy though. And that's a problem. But I think it's just because of the click. I think the other div has the same thing. I don't understand really well why it's happening. I think the click event gets stuck at some point. No, it's just this one. So maybe it's because of the position. So I'll change this later. But you can look here and step forward and backwards. It's pretty fucking cool. It was a lot easier to figure out than I thought it would be. I just created the timeline of the store and then set up all the... Just call the methods on the timeline for the buttons. Oh, fuck. Yeah, I'll focus on this later. I also need to create a button to say if it's directed or not. Because I'm making based on the props, and I don't remember if I created a flag variable. I think I did. On the store to determine whether or not it's gonna be directed. Yeah, much better. And the issue with this is that if the color of the arrow is different, then you can visually see that the edge goes inside of the arrow is not very good. But for now, I think I'm just gonna leave it like this and then just keep the color of the arrow always the same from the edge, because it doesn't matter that much. And obviously I have to fix the other stuff there. I think one of the problems with running C or C++ is that on the course he uses a make file, and he says he suggests choose Ubuntu or Linux, and I don't want to do that because it's gonna be too much work. So I want to figure out a way to see if I can run on my thing, and then I put a file called make C, I think, on the environment variables, but I don't think it's the same thing. I'm not really sure if it's the same thing as the make file. I think it's something that I installed for some reason way back then. I think I'm gonna see on the path. C make, not make C. C make. But it's probably not the same. Yeah. I think I'm gonna open the other project and I'm going to see how he does it, how he does the files, structure the files. The other thing annoying about C is that you need to create header files, which I didn't like that much. I don't understand why. It seems very redundant, because the header file is just declare everything that you're gonna use. I think I already have the extensions. Yeah. I'm just gonna put this code there. I'm gonna see if I can run this stuff. I don't remember if he explains on the course how he gets these files. So maybe this is another thing that I have to figure out. Ask JSON. I remember on the C++ course that I did some time ago that you do two different commands, one for compiling, the other for running, and you use the GCC. But I remember I was using Visual Studio, and I don't remember the commands very well. So that's the first thing that I have to figure out, is how to make this work. Like which one to choose and what is the differences and why it's not working here. Yeah, this part's gonna be the most annoying, just the beginning, getting used to everything. And I think that the beginning of writing the compiler is gonna be very annoying as well. The beginning of writing the lexer, because I'm not gonna understand anything, and then I'm gonna get a bunch of mistakes all the time. And this is the problem. I don't like this very much, because I don't want to depend on an extension to run things. I want to know like how to do it in the way that you're supposed to do it directly from C. And this one runs the thing. And prints here. I just wanna see how to do this with the commands, if I have to pass all of this stuff here. I think just the commands doesn't work, because you need the compiler, and then that's why it's calling all these files here. The question is it worth it to just use this stuff, or... I think the first thing is get to the point where I'm used to like writing stuff and then executing and seeing what the output's gonna be. Then once I get to the point, then I can build something, or yeah, probably gonna build something, and as I build, I look at the other code for the compiler and see how he does it. But it's probably better to build on my own first, because then I'm gonna face the challenges, and I'm gonna, when I study the other source code, I'm gonna understand more the place it's coming from and the differences that we have in the way that we think. And I need to clarify, because I'm not trying to build a compiler, so that's the hardest part. But first I need to clarify like how to build a compiler. I think I need to forget about creating the graph first. Then once I'm more familiar with creating the compiler, then I can think about the graph again. Otherwise, I think it's gonna be too difficult to do everything. And maybe it's a mistake to try to do it in C, but I think it's worth it for now. Because the problem with C is that it's gonna take more time to build it. I think in Python it would be a lot faster. I'm just gonna use this stuff for now. This just run. You can run from this here as well. Maybe first I'll ask how to... Because I wanna focus on more... Like now that I got this to run, I want to focus more on the package manager side and understanding the main libraries that C has. Then I go back to this later and I see. And so just to see. I think this is the commands that I learned. I think it was on Code Academy for C++. Write this stuff to compile, and then you just call the file, because it's gonna create an executable in the same directory, and you run the file. Remember now? Maybe it doesn't work because it's Windows. It already has the executable here for the... I need to put the output file. There we go. And then you just run. So it is very easy. Yeah, nice. But it's a lot better to run from here. Yeah, that's good because I thought it would be a lot more annoying to figure out. The main problem with this, I think with blockchain is the same thing. Is usually because I'm using Windows and everything's made for Linux. There's usually a bunch of different problems to making things work with the environment. It's very annoying. But it looks like it's very easy, so. I think it's gonna be make the package manager. And then there you have the standard library. I think it already comes with the language. I have a single blah blah blah. System package manager. Project specific. I wanna know how to download things. If there's a way, easy way. The same way that you use Yarn or use pip install. And then I think next thing that I'm gonna do is just open a file, try to open a file, and then maybe should copy one file. Oh, actually, I'm going to put the. I'm not really sure. I have to search. The first thing that I'm thinking about trying to do is with the React source code. There is a big issue though, and it is like because a lot of these libraries, they seem like they have some differences between the way that the source code is on the repository and the way that it is structured after you install the library, because it's going to transpile everything with Babel. So the biggest concern that I have is that if I just parse the source code, if it's going to be an accurate representation of what's going on. Because on React, specifically on React DOM, I think that I remember they use some variable there that it says something that if you use that, you're gonna be fired, and there's some React like internal things, and I'm not really sure if they did, like if they do something to hide a part of the code that is not accessible through the repository, but I'm not really sure like if that's would work or not. I remember that I couldn't find the like where the declaration for the file was, and I think it has to do with the import system. I think that's the biggest thing that I have to figure out. Also, the last video I think, or some of the videos that I've done lately for the thing that I'm doing, and I posted on Twitter, someone commented about creating something to figure out Solidity files, Solidity dependencies, creating a graph. And I haven't dived too deep into Solidity import system. And at first, like the way that I responded is because I assumed that it's gonna be harder, because there might be some differences in the way that the process of finding the files work. Because in Solidity obviously is on the blockchain, and I was thinking that it may be connected with the IPFS, I think, system. And I remember that I read on Vitalik's post that he explains how to store things on a decentralized way, but I don't remember really well how that works on the blockchain, because I know they have a system to store images for NFTs, for example, but I'm not really sure if that the storage is actually happening on the blockchain or if it's somewhere else, and if there is some centralization or not on the storage, because there are some problems. And then there's some blogs that Vitalik did, that explains how the process of storaging works on a decentralized way if you're gonna do it, and there's some game theory there. And I'm not really sure if the import system is related to that, because obviously it's gonna be accessing files. So from the brief things that I read, it looks like obviously there's gonna be the difference between the files that are imported locally and the files that use the eth to import, which is gonna be an URL. It's gonna locate the file somewhere. But I'm not really sure how that's gonna work on Solidity, because if you put an URL, it's not guaranteed that the blockchain is gonna have access to that, because the internet might change and then defeats the whole point of the blockchain. So, like, for this reason, I'm not really sure if there is a difference, fundamental difference in the way that the import system works on languages that are incorporated on the blockchain, or if they're the same, because in the compilation process they happen outside of the blockchain. So in Solidity, it just gets everything, then puts everything into binary, and then after that it goes to the blockchain and then it's on the virtual machine, and that's where the differences happen. And so it would be the same, or if the import system is connected fundamentally with the blockchain. So that's thinking about that made me realize that one of the biggest things that I have to figure out is the import system on JavaScript, because I think on Python, but Python is pretty much the same. But Python, I think, is more clear when you have relative imports, because there's also some problems with the relative imports in Python, which are very annoying to figure out. And there's a problem there, and I'm gonna have to study that as well. So one thing is which language I'm gonna start first. I think it's probably better to start with JavaScript. It's either gonna be JavaScript or Python, because most people are gonna use JavaScript or Python. So, but I think JavaScript is probably better, because then it would allow me to also learn the libraries as well as I build this stuff, and then once I figure that out, then I can move to Python. And it's probably going to be very similar. So I think that's the thing. I need to organize my thoughts more, like which direction to go, because there's so many things that I can do. Like one of the biggest things that I'm thinking about doing now as well is to try to find the common denominator. So it would be good if I build things in a way that's like puts me in track to build this idea of the lowest common denominator between languages, because in the same way in mathematics you have like a number 12, for example, and then you have the number 8 and 4, and then you have the common denominator between them, which is true. So languages, I think, are the same thing, where there is a point where they're fundamentally the same, and then there is up until the point, from that point they diverge. And I think it's in the same way that numbers work. So you can have languages that are going to have a lot more in common with each other, which means that they are going to be composed by prime numbers. And then you're going to have languages that are prime numbers themselves, which means that they are not composable based on other languages, and they are unique to their thing. And obviously everything is going to go back to binary, which is the fundamental structure. So the biggest thing, I think, or a very useful thing that I could do is to figure out how to create something that makes it clear the path towards the lowest common denominator between languages. So highlights the tree from the way that they started to the way that they evolved, and put that on the graph, and then highlight the differences on fundamental differences and differences on syntax. So I think that it would be smart to try to create like from Python and JavaScript, and then maybe that's the one reason why it's better to do it with C, the compiler, because I think C is going to be somewhere along the bridge. So I have to think about, as I'm creating stuff to parse the JavaScript and Python code, how I can put together the things that I've built to create this tree that is going to highlight the differences. And I think I need to structure my thoughts so that as I'm studying the fundamentals of both languages and how to extract information, I have a good idea of what are the places that they're going to be similar or different. But the challenge is that it can't be like manual. I have to think about a way that I can do it programmatically. So like how to find and I think that this is going to come down to breaking the languages into data structures, and then figuring out based on the geometrical structure of the languages how to find the differences. So that's the path I have to go. But probably, so, but it's very difficult to think about. So I guess the question is, I'm probably gonna start with React first, the React project, and so start with the React project. And as I try to parse the React project, I try to break down JavaScript. I guess this is the question. Is it better to break down JavaScript first? And then, because I'm gonna have to break down JavaScript anyway, in order to build the parser and the lexer. It's just gonna be breaking down the language into the fundamentals. But I guess this is the biggest thing. This is one of the main points of confusion, is how do... And this is what is making it hard to think. So I need to clarify this more. Because there is a fundamental difference between like this idea of trying to break things down into the fundamental and building the compiler. I think that they are different. So if I just focus on building the compiler for JavaScript, building the parser and the lexer, it isn't necessarily going to allow me to find the most common denominator, because I'm not going to be paying attention to like the fundamental things that build the language. I think this is the problem, is that like in the same, like I don't need to know how assembly became C or how assembly became JavaScript in order to be able to create something that gets JavaScript code and understands it and translates it to binary, if that makes sense. So the question is how to clarify this difference. So for example, I can build something like, say I was doing this in Python, I can just put like a string and I can do this, and then let's say I'm receiving like st is the variable of the file that I'm parsing. So this is gonna check if there is this symbol in the file, and then if there is a symbol, I can append like to an object array, something like that. And then like this would allow me to create the logic that is gonna translate the code of an object into the abstract syntax tree, and then later on execute this code. But it doesn't say anything about where the objects come from. That makes sense. But there is a crossover between them, and that's what I'm trying to... I think that's what I'm trying to figure out. Because if I can build the logic of breaking down this into the abstract syntax tree, and at the same time highlight where the thing came from, like build things in a way that is gonna allow me to tell how the thing is constructed at a lower level. This is the thing. There's also the difference that there's a difference between the way things evolved and the way that you can redo them. That's another thing. So for example, let's say JavaScript. JavaScript came from assembly and from C++. But nowadays you can build JavaScript using Python, for example. So, and I think that's not necessarily what I'm... Yeah, what I'm concerned is not so much about the history, but maybe the history would be nice as well, of the things that... the way that it was actually done, because this is the problem. The history allows you to highlight what potential problems might be and what potential assumptions were made. What assumptions were made to build the languages in the way that they were. And this allows you to have insight on the distinction between what is fundamental and what is superficial difference, because the assumptions are going to highlight what the superficial differences are. So you can imagine that if I build JavaScript using Python, I build an interpreter in Python that executes JavaScript, or I build an interpreter in assembly that executes JavaScript, if I look at the differences between them, it's gonna be easier to highlight what's fundamental about JavaScript itself, because the language that I'm using is different. But it's not gonna allow me to have a very good insight on the superficial parts. But maybe not, because the superficial is gonna be based on the way that things were actually built. But I think it probably doesn't have anything to do with the history. So the question is how to understand what is fundamental based on the structure of the language itself. I think that's the point. The reason why I'm confused is because I don't know this stuff very well about the grammar and the terminal and no terminal things. So I guess I need to study this more. Maybe I'll study this now. I need to understand this to know like what is fundamental and what is not. I guess the superficial difference is going to be the syntax, and the fundamental difference is the way the syntax is going to be executed. But and the question is on the final parts, after they become an abstract syntax tree, how does it execute the commands? So let me think about this. I'm gonna be right back and I'm gonna think about this. But I'm probably gonna build something now. I try to build something simple with C that just opens a file. I think the main goal today is probably to open a file and then try to read the file and see if I can at least get some pattern out of the file. Then once I have that, then I think I'm gonna go back to this other like more lower level way, and I'm gonna try to bridge the gap between the two. But the first project that I'm gonna start trying to parse is React probably, and I think I have here somewhere the React source code. And I think what I want to understand is what I want to focus on making it easier to understand is the lanes and the scheduling. They are related, obviously. It's not the. There was something else. There are two different types of flag variables that they use. One is the lanes that it specifies if you have a concurrent mode going on, then the fiber is gonna perform work at different parts, I think, and it's gonna flag the work differently. And the flagging of the work and what's gonna be done at each time is gonna depend on the lanes. So the lanes are kind of like global variables that are binaries that are gonna decide based on the control flow of the fiber work loop, what's going to be updated first. So I want to clarify that. And there was something else that I think, but I'm forgetting now. I remember there were two types of variables that were hard to understand. And the reason why it's hard to understand is because if you just go over the source code manually, the variables are global variables. So you have to go back and forth between the files, and it's very annoying. So I think that's the main thing that I want to build first, is how do I figure out everything that happens with the global flag variables on React to understand the lanes more efficiently. So I think React is a good like prototype for everything that I'm gonna do. But I want to build the compiler in a way that is gonna allow me to understand like what is fundamental about JavaScript and what is superficial. And I know that one superficial thing would be, which also is really annoying to me, but is understandable, is just the declaration of the function, for example. So I don't think there's any reason for, in Python, the function declaration is def, and in JavaScript is function. So, and the reason why it annoys me is because these kinds of things just makes everything harder to learn, but they don't add anything fundamental. And it's kind of the same problem that I have with TypeScript, which I think TypeScript is the gray line between these two paradigms, which is that the reason why like I don't like TypeScript is that it doesn't make the code faster. So there isn't any fundamental reason to use TypeScript, because from the computer's perspective it's always the same. So the main argument to use TypeScript is because of developer time. So when you're working on a thing, to make it easier to clarify. But I think that this goes to the other extreme as well, because if you're forced to specify a type on everything that you do, then the code becomes too verbose and there's too much additional work and too many things outside of your control that it makes it harder and not more productive. So there's diminishing returns. And I think this is going to follow a Pareto distribution or a log curve on the amount of typing you're going to have. There's going to be different based on the variance of spacetime, because it's going to be dependent on the structure of the code and where it's deployed. So the amount of typing you need is always going to be dynamic, and I think the solution is going to be anywhere in the middle. So a typing system that allows you to add types only when you think that it makes sense. And that's always going to vary based on the context, because everything is going to be different. So I think that the typing system is on the middle way between this distinction of what's fundamental and what's not, because for the most part, code is also a projection of the way human beings think, because on the binary, it doesn't have any fundamental structure. It does have a fundamental structure in the sense that you're capable of encoding information. So there's a fundamental property of the laws of physics. Without going in epistemology and all of the other stuff in philosophy, there's a fundamental property that you can arrange the electromagnetic field with information based on symbolic representation, which is the coherence of a network, which is the way human beings construct symbols in order to coordinate on space-time. So each character is a symbol, everyone has a representation of what the symbol means, which is always going to be different, but it seems to be consistent because of the laws of gravity. So computation is going to be the synchronization of this symbolic representation over space-time by using the electromagnetic field to encode information. And that's how you can put things on the screen. So it is fundamental in the sense that you can build stuff, because you're arranging the electromagnetic field based on geometrical properties of your experience, which is our perception. So you're encoding geometrical structures into the electromagnetic field based on the manipulation of the impulses, which are the binaries. But the part that is superficial and not fundamental is that when you construct everything based on these geometrical structures, you're gonna embed meaning of concepts, because you're embedding the meaning of words. But maybe it's fundamental as well, because you're just like, what you're doing is creating a multifactor geometrical structure. There's gonna be a language, which is just the relative nature of different geometries interacting with each other that seems to become more complex. Like geometry changes in such a way that it seems that it becomes more complex over time from the reference frame of an observer. So it seems like you're putting different geometrical structures together, and then you maximize energy by attaching the meaning of the whole construct into a concept. So for example, in a computer, instead of thinking all the parts of the computer, like cables and the screen and the LEDs and everything like that, you encapsulate everything into a concept and you call a computer. So you don't have to think about all the other parts. So you're composing different geometrical structures into a higher level one. And I think that's what programming languages are. And the path towards the construction of the concept is the thing that is going to be superficial, I think, because it always depends on the context and the culture that creates the code, which is going to be construction of symbolic representation over words. And I think that this makes it so that the languages naturally evolve to create infrastructure and culture and libraries that are going to represent what the symbolic representation of the language builds. But the question is, how do you figure out if it is just the syntax that is changing, or if it's like a fundamental way that the memory and the speed are going to change on the language to favor that. So like, is it a self-fulfilling prophecy that it's kind of like what would be a good analogy? Like, for example, is Python good for AI because people that gravitate towards Python like AI more, and then they build libraries to solve AI problems, and then Python becomes the language for solving AI problems? Or is it there a fundamental thing about Python that makes it better to solve AI problems, and then because of that, people gravitate towards it when they want to solve that type of problem? And I think that is very hard to know, like the direction of cause and effect there. because I think there is an element of self-fulfilling prophecy, and because of the nature of social structures, it's going to be like groupthink. So as soon as it gets gravitational force, it's going to increase exponentially because of the nature of social networks. So I think that for the most part, there's going to be several different assumptions about the languages that don't hold down to the fundamental principles that are grounded in the laws of physics. So I think I have to think, like, build the stuff thinking about this. So, but I need to clarify how to actually do this, to highlight the, like, is Python actually good for AI, or is it because of the culture? And what is the difference? How do you highlight the multifractal boundary that is going to separate the fundamental, the funnel of information that has the illusion of fundamental and superficial, that creates the geometrical structure of the language? So I'll be right back. I think after I figure out how to read the file and parse or get a pattern for a simple string, I'm gonna focus more, like I'm gonna do something more light or lighter to like familiarize myself more. I think that's probably the best thing to do. Because otherwise I think I'm gonna get frustrated trying to build everything in the beginning. I also think it's not very effective because I'm not gonna know really well like what to do or how things work. I think I'm gonna delete this one. I'm just gonna run code with the thing there because it's easier. The commands. Oh, I think, yeah, that's what I was gonna do before. I need to figure out, I think I downloaded here somewhere the source code for React. But if I didn't, I'm just gonna go there. I think I'm just gonna download. I'm gonna put it on this file and just gonna put one file instead of this. Let me think. Oh, I forgot to show the link. Let's just close here. Maybe it still works. No, it doesn't. Oh, here. Yeah, so I put this link here. I think that's what I'm gonna do. Because I need to get 10 people to use it on my website. So I'm just gonna do some clickbait, I think, to tell them that there is a surprise when you click the link. And it's just gonna be recall this song here. And I need to fix this shit as well. Yeah, I'll think about this later. Probably gonna fix the other stuff off stream. Because it's pretty unlikely that I'm gonna be able to figure everything out by Monday, I think, on how to parse everything and how to have something useful. So I don't think it's worth to like stress about the build space updates. You're just gonna focus on building the thing in the way that I think is best. I was gonna search for a React source code. The thing is, I'm not really sure if I just focus on building the compiler or the interpreter for both JavaScript and Python. So build for JavaScript first and build for Python. It might be just a waste of time because it might be more effective to think about a way to build it in the way that it's gonna allow me to figure out what is the fundamental like difference between them. So I guess this is the question: is how do I parse everything while trying to highlight the fundamental differences? And I guess this is the reason why I'm conflating the other thing, because maybe this is the bridge between the two. Because the fundamental thing is gonna depend on the history, I think. That's the question. I think this is the thing that I have to clarify. Because in a way it does depend, but in another way it doesn't. So I guess I have to clarify all the way. The course is only up to the parser, but then after the parser there's other steps. Obviously to run the code, so maybe I need to figure out up until the code. And maybe I should forget about the history and just try to do the whole thing and then visualize until the very moment that they both become actually binary instructions. What is the hierarchy there, I think. So maybe the best idea in the beginning should just visualize the path of translation. So let's say you have a file in JavaScript or you have a file in Python, and then when you deconstruct to the lowest level before it becomes binary and it's going to be executed, what the trajectory of both would look like. So from the high level instruction, what becomes when you branch off. And then from that point, I think about it, how to highlight the differences. But I think the history has something to do with this as well, because I was thinking more about like, but maybe it doesn't. I'm thinking about from the binary to JavaScript or Python from the previous languages. I think it's because of the lowest denominator I talked about. I think it makes it easier to understand things if you think in terms of the trajectory in history. But maybe not. Yeah, the question is, at what moment do they diverge? So, is the difference in the way that they're gonna become binary, or is the difference only in the amount of stuff that becomes binary? I think it's gonna be both, and it's gonna be in between. So, like, there's core set of instructions that are the same, like functions, if else, statements, loops. And the stuff that is going to change when it comes to that is just going to be the syntax, I think. But maybe not. Maybe there's more differences. What is annoying about that is that if it is just a like superficial difference, is that if every language had the same syntax for all of this stuff, then people wouldn't waste a lot of time. Like, it would be a lot easier to know a bunch of programming languages by default, because all of them would have the same syntax. So I think that there are fundamental reasons why the languages change, it's just hard to know how those fundamental differences are how much they are influencing on the syntax itself. I guess this is the thing that should clarify. I'm gonna put the folder on the top because I'm probably gonna create other projects here. And then I'm just gonna copy one file of this project into the other one and try to read the file that I copy. And it's a lot of stuff. This is something that is concerning me as well, because it's a lot of things that I have to study. This is the problem I had since the beginning, is because I don't know how hard it's gonna be. I know that there's a bunch of things that I have to learn, but yeah, I'm not really sure if it is even like possible for me by myself to do everything. So because there's so many like different things that I have to think about and build. And I know that for the course that the guy made on the compiler, he said it took him an entire year to build the course. But obviously it's a lot more work because you have to edit and everything like that. But even if you compress, let's say for into 4 months, it's still a lot of time. Like 4 months to build everything. And that's just the compiler. It's not even talking about the other languages and the differences and all of that stuff. So this is the biggest issue. Because I don't have a lot of clarity on the time and how hard it's going to be, it's very hard for me to create a hierarchy of values that is going to allow me to prioritize what I have to do first. I think the shared files are the ones that have stuff about React that might be not accessible through the source code here. I think this is one issue with the JavaScript. Maybe it's better to start with Python first, because with JavaScript I'm gonna have to think about the Babel transpiler. But maybe this is a good way to start as well, like to highlight how the source code differs from the Babel. So highlight the Babel process. Maybe I should start by studying the Babel thing and trying to see if I can highlight something there. Yeah, there's some weird stuff here as well, because I think they use JS doc or something like that. I remember there is a name somewhere. It's another tool I think that they use. I think it's Flow something. Flow fix me. This thing here that allows them to put some types. So it's not completely JavaScript. I'm not really sure if I'm gonna be able to do this stuff. It's sure hard. The main challenge is time, obviously. I think I can build everything, but the question is how much time it's gonna take for each thing. So let's see on the other projects if we did this. I didn't have the time to watch the course again, but I'm gonna do that as well to understand what he does it in the beginning, because I speed ran everything. because I had the other course to watch and a lot of other things to study as well. So I just went through everything at high speed. So if I remember, he uses something. Yeah, he creates this file and then he builds a bunch of commands here. Maybe I should do this off stream, because it's gonna be easier when I go over the course. Because from what I remember, he runs some command here that based on this file is gonna run some things, but I didn't understand very well how it works. I think it's just a file that is gonna determine. So instead of running like a file, it's kind of like in Python, where you should have a main file that has all the functions and everything. And then instead of running each file as a script, you run the entire thing by having that file. So I think this is that file where it has everything that is gonna run. And then you run this file instead of running the file directly from here. I think that's how it works. And this is just a bunch of shell commands or commands line arguments. It doesn't look like he has anything related to include or libraries like the thing says there. So let me build the. I'm gonna forget about this stuff and I'm just gonna try to build this simple thing on the file. So yeah, but the problem is that I might have to do that because I might need a library. But I think probably there is a function or something that allows you to open a file from the standard library. I would think. Yeah, definitely there is, because like C, it depends, I think. But I'm pretty sure that there is something. It's even more likely than the other languages because you can build the operational system on C, so it makes sense. Like on the other video that he does everything, the main question is that like maybe it's possible to build the operational system with other languages, but I don't think this is done very often unless it's like lower level, like assembly, and he builds a bunch of things on assembly as well. But he uses C to build the file paths, so obviously there is a standard library in C to handle this stuff. And the file system is just a bunch of algorithms that are going to determine in memory the information of the file. So there's a bunch of metadata that you program to specify what the file is going to be, like the description and everything, the format, and how much you're going to put on the memory, and then is stored on disk. And then the disk communicates with the RAM through some virtual thing, some virtual file system thing. And based on that, you can create a file path. You have a path resolver, which assigns a path to the file in memory and then stores the metadata of the file. And then you go back and forth with a buffer from the hard disk that contains the memory for the file and the reading thing. And I remember that I think, yeah, he created the commands himself. So, but it's probably parts of C, normal C, like on the standard library. But he created the commands to open the files and to, I remember now, to, which is based on this path resolvers and everything. I think it's F open. the name he assigned, but I don't know, like if on the standard C, if he wasn't building everything, if the C already has the functions. But I'm pretty sure that it does. Or maybe using C would be better. Something I think as well that's like I've seen on Twitter people talking about that they can, it's already possible, and I think it's going to be more and more possible, obviously, for there's a lot of people that are running code and don't understand what they are building because they can build everything with AI, and they're just doing the prompt. I'm not really sure how to say that, but they're prompting AI, and then the AI builds everything for them. And in a way, I think that it is good that this happens because it makes it more accessible for these people to do it, but at the same time it's very problematic because, and this is another argument that I saw, which I think it doesn't make any sense at all, which is that like a super powerful AI is not gonna take control of everything because the smartest human beings on the planet are not the ones in control, and like intelligence doesn't necessarily correlate 100% with power. But this is I don't I don't like this argument at all because it makes things a lot worse actually than better if that's the case, because then it means that you're giving a gun to a child pretty much. So, and this is the biggest problem because, and I do think that this is the case to some extent, because the person that has the intelligence to build something is very unlikely that they're going to misuse that thing, because since they had to go through the challenges to be able to build that thing, they understand it much better, and they're going to understand the consequences of using that thing, the consequences that it has, and like the risk-reward ratio of using it. So they're going to be naturally more responsible, I think, because they're more invested into the things that they built. And then it becomes really problematic when you have something like some people create some really powerful stuff, and then someone else can use that really powerful stuff without having to go through the process of building themselves, because then it becomes much more likely that they're gonna misuse that thing. And I think this is the same problem with code. What you're gonna have is just more and more people building a bunch of code that they don't understand, and then it's gonna create a bunch of systems that nobody understands what's going on because it's too complex. And then once something breaks, then everything breaks down, and that's the problem. So you can build a whole business just by prompting AI, and that's going to become more and more normal, I think. But the issue is that you're not achieving anything. The only thing you're doing is just becoming like more a slave to the systems, because you're creating a more complex world that you don't understand. And like it's like one of those things where it's like short-term pleasure, but then long-term you're fucked. But it is a good thing in a way, because obviously like there is a gradient to everything, I think. So I think that the best way to go about it is to do what I'm doing probably, which is to use the tools to allow you to build better tools to understand what you're building, and then you improve yourself. Like you put the power back on yourself instead of putting the power on the system. But obviously this has limits as well, and it can be a slippery slope because of transhumanism, which I think is the problem with Neuralink and other stuff like that. That like, are you sure you want to become like a cyborg or something like that? And then there's a bunch of philosophical questions about this. Because obviously the best way to learn is going to be to put AI into your brain, but then are you really that person anymore, or you're something else? I think you're something else, and I think that this is The thing that people don't understand about downloading yourself into your hard drive is that it is impossible. By definition, you can't download yourself on a hard drive because your experience of yourself is the present moment, and in the present moment, you're not on the hard drive. So even if it is possible to put yourself there, it would change your experience of the present moment in a certain way that you would become something different. And it's the same thing with cloning yourself. Like when you can clone yourself physically, but then it's not going to be the same because the definition of what you are is the nature of the present moment, which is unique because it's self-evident. It's already here. So I think that, yeah, it is a good thing for people to build, but at the same time, it's very dangerous because of the reasons I just said. I think that's what in this, like, it doesn't make learning how to code less. Not really sure what the word would be, but it makes it more necessary and better to learn how to code, not less, just because you're going to be replaced by AI. Because the world that we're going to create is fully dependent on software. Like, I think software is going to consume reality, and everything's going to be connected through the network. And this is one of the reasons, I think the biggest reason why we should try to create a blockchain as fast as possible that is capable at least of trying to approximate alignment to the best degree possible, because everything is going to be connected. And then the biggest question is, who is in charge of the connection? So who is in charge of the systems? Who is in charge of the self-driving cars? If it's just a company, it's gonna be very bad because companies are not aligned with the nature of the whole. Because of the structure of market economy, it becomes a self-fulfilling prophecy that is out of balance because the incentives are misaligned and the power gets corrupted, which becomes a vicious process, which becomes through gravitational force an exponential distribution. And if there is no regulation, then it doesn't dissipate the energy. And over time, it just corrupts itself because you can't have centralization without decentralization. So things become like more and more centralized because one company owns everything, like owns reality. But when they own reality, they don't own anything because what defines the company is the environment that makes it possible for the company to exist. So by consuming the entire environment into itself, it destroys itself because it's inconsistent with the laws of physics. And I think this is the problem with Nazism, is the idea that the only thing that matters in life is being the best, because there isn't best. As by definition, the best is always relative to a reference frame. And what creates the reference frame is the nature of space-time, which is the nature of information. So the best path, I think, is to try to create a blockchain that is going to encapsulate the optimal distribution of decentralization to centralization relationship to the complexity of the environment. But the challenge is, how do you align the incentives? Because there's going to be an infinite amount of incentives, and the biggest question, I think, is how do you find the boundary of self? And I think there's a very interesting podcast that I listened to, and let me show. This guy is a genius, for sure. And he talks about this, and I thought it's very interesting. Which is related to the prisoner's dilemma and the computational boundary of the self, which I agree very much with what he says. I think one of the biggest point that I watched the George Hotz debate with Eliezer. I think the biggest point that George Hotz is missing from the prisoner's dilemma is the same point that people miss about mathematics, is that because something becomes so obvious to you that you use it all the time, you forget that there are hidden assumptions that you made to create that thing. So the framing of the problem already has the assumptions that you projected into it. So saying that the prisoner's dilemma is unsolvable, it's already falling into the bias that you don't realize that you're projecting your assumptions over the problem that you created. Because it's a different thing than just thinking about chess, because chess has constrained rules. But if you're thinking about realities, you're always going to be projecting to some degree the framework from which we're trying to understand. And it's the same problem I have with the question of why there's something rather than nothing, because the question itself already presupposes that nothing is different than something. So there's already a bias, and then because you phrase the question that way, it becomes impossible for you to see the answer. But if you frame it in a different way, and you realize that the only reason why nothing exists is because something exists, so the distinction between the two is our perception, so they are the same, you realize that the question is meaningless because there isn't something rather than nothing, because they are the same thing. So I think it's the same issue with the prisoner's dilemma. You're presupposing something based on your assumptions over what the game is, and then based on that you're arriving to conclusions that are not necessarily true or necessarily accurate. And I think that Eliezer probably understands this. But the way that this guy puts it, the Michael Levin, I think is I think there isn't a absolute right approach, but it's probably closer to accurate, which is that he says that there is one thing that the prisoner's dilemma doesn't take into account is that agents can separate themselves. So there's an animal that you can chop its head off, and then it becomes two different agents. And then that makes the structure of incentives a lot more complex, because the nature of goals and strategy is necessarily related with the perception of self, because you only do things related to what do you think yourself is, to the boundary of yourself and everyone else, and that defines your behavior. So if you take into account that agents can become two different entities, the same agent can become two different entities, then it changes the game completely. And I think that reality is much more likely to be that way, because the boundary of yourself to everything else is just an illusion, which you think is the body, but you can't exist without the environment, you can't exist without food, without water. So you are everything that surrounds you to a certain extent. And what you think is yourself, which is the model of the abstractions you create, is just an illusion, because it's a byproduct of the systems in your body that are creating your thinking, which have to do with the way that you eat and the way that you breathe and the water you consume and everything, and culture, everything like that. And I think this is the challenge, like this is the path to alignment, is to figure out what is the multifractal boundary that achieves a relativistic Nash equilibrium based on the distribution of power in a network. I'm trying to find out the podcast that if I look in the other browser. I'm searching for the podcast that I thought it was very good because I want to show. Oh, fuck, I'm not finding it. Oh, here. Yeah, I highly recommend watching this one. I'm subscribed to them on the other channel that I have, but it's very good. And I think this is the path, probably. So the question is, how do you define the boundary of self in a way that it's gonna create a structure of incentives and goals that is gonna be in alignment with the whole, so achieves balance overall, because not a single agent is gonna evolve in a certain way that is gonna gain power in a way that it breaks down the structure of everything. And obviously this has to do with the biochemistry of each one as well, because it's not only how you define the self, it's how does that definition of the self accumulates power over time. And I think that this has to do with computational frequency. because it's the computational frequency of the network that is going to define the relativistic boundaries, and it's going to define how an agent in relationship to the relativistic boundaries is going to acquire power over time over the network. And I think it has to do with gravity and mass. And in human beings, the hardware is not sustainable because it evolves to an exponential over time. And I think that the best way to solve this is through the blockchain, probably. But the issue with the blockchain is that, and this is another question that I have, that is kind of is actually very confusing to understand because of the boundary of the self, which is that, like, you can think about an AI model as being the weights and biases that define the model, or you can think about it as being the network that puts data and puts data in and out. But then, like, how do you define, because the substrate also matters, I think. So is it possible for an AI model to translate itself into a substrate that is outside of silicon and just create something that is more like biological, or not biological, like more carbon-like? And based on what I've heard from Eliezer, I think that he thinks it is, but I don't understand really well the nuances of that, because then how would you define what makes up the nature of self of the intelligence? If you translate an AI model for something that is carbon, how you would translate itself in a way that you would keep the sense of self that the thing has. And I think that the reason why this is important is because that's the biggest problem I have with blockchains, because they say that they are decentralized, but they're not decentralized because they rely on the whole infrastructure of the network of human beings. And if you want to create a blockchain protocol that is going to try approximate a balance, is going to be, you're going to have to go beyond you're going to have to create something that goes beyond the network, that doesn't rely on the infrastructure to be correct, because the essence of the network itself is grounded on the laws of physics and not on the infrastructure that human beings have. So this is the thing, is that it can't be bounded by hardware that human beings create. Like, in the same way that you can create a compiler for a language based on the same language, so you can create a C compiler for C that compiles C. You can write a compiler in C that compiles C, but so it doesn't necessarily need to start off not depending on everything. But I think that's and this is the core of the question, like, is it possible through the nature of AI models to create a network that over time the network becomes unbounded by the infrastructure that created it, because it's bounded by the laws of physics and the protocol of communication of different agents in the network, and the incentives of the agents in the network converge towards a balance in relationship to power over time. I forgot how to print stuff. Print off. And this is something I realized as well, not that long ago, is that and through the model that I also read a bunch of Eliezer's blog, which are very good, but it's very hard to read because there's a lot of stuff he wrote. And I think he's a very intelligent person. So like all the stuff he wrote is very complicated to understand. So it made me think, because I don't really know, obviously, if the way that I'm thinking is the best way, especially when it comes to the epistemology. He has a series about epistemology, and that was really hard for me, and still is, to think about this, because like in the way that I think now, I think it makes sense, but it might be a bias that I have over the stuff that I built over time, in the way that I think. But the way that I'm thinking now is that, like, what a paradox is, like the nature of space-time is perception over a computational frequency. So perception is symmetry, because you have the fundamental distinction of self and no self, and outside of self, which is an illusion. And that creates a multifractal boundary that is the relativistic nature of these symmetries converging towards higher or lower levels of symmetry, which are also an illusion. And the illusion of the conversion is the computational frequency of a network, because it's the same way that binaries become words. And the laws of physics itself is the coherence of the network that creates the symbolic representation, which is the multifractal geometry of spacetime. So the computational frequency determines the boundaries between things, which are multifractal by nature, because they are relativistic symmetries interacting with each other, creating the multifractal structure of geometry, which is the frequency of awareness, which is computation. So you're reducing infinite potential into the illusion of finite space through time, based on computation that creates this nature of relativistic symmetries. And then based on that, I think that the highest approximation of a truth, and when I say truth, it means lies as well, because everything is a symmetry. So everything you say, everything you think is going to be, there's going to be a symmetry projected into it, because you can only define something in relationship to what is not, or in relationship to what is the opposite. So lies are truths, because they are also a geometrical object, and the highest truth would be the meta realization of this distinction, which I think is the paradox. So, and this is the reason why the paradox is the highest approximation of equilibrium or truth or whatever, is because it encapsulates something that doesn't exist yet, which is the relativistic polarity between them. So the paradox is at the boundaries of perception, which is a multifractal geometry. And this is the reason why they are not logically consistent, because they go beyond logic, because they are right at the boundary of the perception of a reference frame that creates the multifractal geometry of spacetime. And this probably has to do with the blockchain and the network. This is the reason why I think that I spend a bunch of time, and I still am thinking about this, because it's a very tricky thing to think about because of the epistemology of this. Because the question is, how do you create, like, if this is the case, then everything that is computational, like everything that you perceive is a computation, and it is like the essence of spacetime, but then it's a self-fulfilling prophecy. And what I was thinking about is the problem of causality, which I think in some of his blogs he speaks about that, and I think it makes a lot of sense that, like, if it was possible for something to, from outside of the spectrum of causality that exists, to come into the spectrum of causality that you are, you would perceive that the moment you perceive that, it is already a part of the spectrum of causality that you exist. So it's always going to be a self-fulfilling prophecy, because you're always trapped by the boundaries of the spectrum of causality that it is your experience of the now. So this makes me think that maybe this way that I think is wrong, because but I think it might be correct. But the question is, like, how would you know, like, what is the boundary? But maybe that is the answer. Maybe the paradox is the answer, because the paradox is like right at the boundary between is a singularity point from which you can't go over, because it's kind of like the black hole. Black holes are the paradoxes of reality, because they encapsulate the infinite amount of potential that exists between the relativistic symmetries that create the illusion of spacetime, which is a multifractal geometry. But then I guess this is the issue, because this is the question of singularity, because then how is it possible to define the paradox? Because The definition of the paradox is already embedded into the spectrum of causality, which has the relativistic polarities that make the paradox. So in a way you can say that this might not be the case, because if it was the case, then the paradox wouldn't be part of the thing. Like, you can't conceive of the paradox because it wouldn't exist. But maybe that is the case, because then it's related to the computational frequency, which I think it makes sense. Because like the paradox itself doesn't exist, but the perception of it does, because it is defined by the perception. The paradox defines the perception, which is the relativistic symmetries. Just want to copy the code and see if it works. I think this is the thing that I mean that is good, like for ChatGPT, because then you don't need to. It becomes easier, but then the problem is if you write the code and you don't understand what's going on. I think that's the issue. So it is good that people can write, but then it's bad because they don't understand. And the biggest issue with that is that because of human nature is going to follow the Pareto distribution, so most people will fall into rationalization, and they will become weaker over time. And then it's going to create this paradox where the reality gets more and more complex, people get more and more lazy until something happens that breaks everything, and then it is like destruction. But maybe that's just the way that it works. But obviously that's not good because you are alive, so you want to survive, so. Or maybe show up that file. Oh, file doesn't. Huh, interesting. It's not that hard actually. Just puts. The hard part's gonna be thinking about all this other stuff that is more. And I think it's always the case. Like up until this point, from creating the project itself as well. The hard part's not the code, it's thinking about how you're gonna put like all of this other stuff together in a way that makes sense. Because it's based on the laws of physics and what's fundamental. And I have to get used to dealing with this as well, like dealing with memory and then thinking about like how to specify each thing, the size for each thing. So obviously what I can do next is just ask ChatGPT, find a pattern to think, to... Oh, interesting. So I find a pattern to extract out of the file, and then start from this point. I think I'll be right back. I think the size of the word here is gonna be how much it prints, because it's how much is storing from the text of the file here. I'm not really sure what fscan is. Can I find this out? I don't know why in C they write it like this. I hate it. I prefer much better this way here. Because I think the other way wastes a line, and it's more confusing to understand. But obviously doesn't matter. Just a small thing. Yeah, so I'm gonna look at the definition of this. I'll be right back. I'm gonna spend 1 more hour here. The question now is, I think it's not gonna be very. I think I'm gonna change the title of the stream because it's not gonna be very good to. It's not that hard here. So what I can do is obviously just put like some logic here to try to start getting the characters. Maybe the next thing, like the last thing that I'm gonna see is how to get the words. But I think this is already a word, so it's not getting the character, it's getting the words based on these functions here. So I can ask ChatGPT to get the character or the line instead. Then based on that, like based on this, obviously I can create logic that is gonna define. But to create that logic, I think it's better to wait until I review the other course and I look at the. I'm gonna review it, but this time I'm gonna go slower and I'm gonna follow along the instructions to see to build on the same project here, how he did it on the other one. To build the file that is gonna run everything and understand how the file works. But the problem is that he is using Linux, so it might be different, but then I'll figure out. Then I'm gonna follow like the path he went, and then I try next time to do it like on my own without the course. I know he uses several different structs at some points, and he uses the structs and flag variables that are gonna determine whether or not the strings are have certain patterns. But then he does some stuff that I don't understand quite well why or how it works. Because like he does basic pattern matching, but then how does he make sure that that pattern is not incorrect on other situations, or how the patterns don't overlap? I think that part was kind of confusing. So I need to review obviously the course, and based on the review, I will build the stuff here. Obviously, the next thing that I'm going to do is just try to break this down into lectures and then build the parser. Build the abstract syntax tree, try to parse one file first. And then after I do that, then I can try to create a file, graph out of that. And I'm going to think more about how to clarify the difference between, how can I build this stuff in a way that is going to allow me to clarify the difference between Python and JavaScript. I think maybe it's probably better to, instead of trying to parse everything from the first thing that I do is to try to make something that is going to be allow me to understand React, the flag variables on the source code. Instead of having that be the first thing, I should start with just parsing one file in JavaScript and then trying to parse one file in Python. And then once I have the code that parses both of different files, then I can think about the fundamental way, or a good way that is going to allow me to highlight the differences between them and what is fundamental and what is superficial. And then only from that standpoint, I will build the other stuff because then I'm going to have in mind as I build the more complex stuff to parse everything else, like what is necessary to, how can I build things in a way that is going to allow me to see later on to create this difference between them. Allow me to create a graph that highlights the difference between the languages. Because the way that I want to set up, I don't want to set up something that just allows people to see the difference between Python and JavaScript. I want to set up something that allows me to get any language, compare any two languages, and then quickly highlight the fundamental differences between them and the superficial differences. That's going to make it a lot easier to learn everything. That's the goal, I think. One of the goals. And the other one is to build, deconstruct the project. But I think the goal of seeing the differences between languages is harder, so it might be better to do the other projects first, so I think this path is probably better. But I think now what I'm gonna do is just use ChatGPT. I'm gonna change the title of the thing, and I'm just gonna study this stuff here. I need to understand more about the grammar and the non-terminal and terminals, and the whole logic behind. I think I need to watch the videos again, like some videos about this, and clarify this more. The biggest thing that I'm confused is like how do you define the constraints of the grammar, and how does that relate to the other stuff? Because on the course he doesn't talk on the C compiler course he doesn't talk about anything about terminals and non-terminals, but on the other videos they talk a lot about this. And I think it has to do with the way that you're gonna create the abstract syntax tree, the algorithms that you create, and obviously it has to do with the lexer, because it's gonna define the way that you separate tokens. And the hardest thing that he says that on the course, the hardest thing to do, he says, is to build the order of operations in the same way that the mathematics works, where addition comes last and first is multiplication and division. So he says that that's the hardest part, but he doesn't talk anything about the grammar. One thing I've seen a lot as well is people complaining about how ChatGPT is worse, but I don't see any difference in the way. And I think it has a lot to do with the way that, okay, instead of thinking about the problem with ChatGPT, it's just a way you're thinking about solving the thing. Because I think most people, and I was like that before I started learning how to code as well, but the more I learn on my own how to code, the better I think I become with this. Is that your first instinct is always going to be to give up after the first try. So usually what people are going to do is just search for a high level thing, like how do I build a application, and then they expect the ChatGPT to break everything down, and then it doesn't work, and then they quit. And the reason why this happens is because their limbic system, which is the animal part of yourself, is the part that controls your emotions. I view the limbic system as the bridge between your animal self and your conscious self, because it's like in the middle of the brain. And the way that I think about it is like your feet is on the third dimension and your head is on the fourth dimension, and you're a funnel between them, like a feedback loop system between them. So the base of your brain is for animal instincts, and the more you get closer to the forehead, the more it becomes the conscious part of yourself, which is the abstraction, and they're codependent because they only exist in relationship to each other. So it's just a distribution of geometry. But your animal self is always trying to make you rationalize things and create ideas and identity that are gonna make you spend less energy and take less risk, because the way that genetics evolved in space-time, which is the problem we have, that is not flexible enough, because we still think like animals even though we created a different world. So the feedback loop system is out of sync, because we create technology that shapes the environment, and then the environment changes, but our biology doesn't change at the same rate that the environment does. So DNA is lagging behind, and because of that, it becomes out of balance. So most of the problems people have nowadays is that their conscious self understands that they are on a different environment, but their animal self doesn't. So your animal self always makes you have ideas that are going to justify you not thinking in the rational way, but the rational way only exists in relationship to the animalistic way. And then it's going to create a polarity between left and right that people are going to deviate through, because it is more comfortable. And I think that's the essence of gravity. So it picks up gravitational force over time. It makes you rationalize, and because of that, people are going to stop. But I think that the best thing to do is, obviously, I think the most important is probably self-awareness because of that. Because the more self-aware you are, I think it's not worth like fighting against it, because it's not a bad thing. It's like being on a diet or not. It's not bad or good. It's just a matter of values. And I think what awareness allows you to do is to be flexible in the way that you fix your behavior based on what you think is in alignment with you. And I think it's the same thing here. So it's not about like fighting and becoming upset that the thing doesn't work. It's more about having a self-awareness of when you're rationalizing to not do the things you know you should be doing. So when you ask a question and you don't get the response you want, I think that the first instinct is going to be to blame on the thing. But then the more self-awareness you have, the more you're going to start realizing that that's what you're doing, and there's a part of yourself that's making you do that because it's going to gain some stuff out of it. And it's the same thing with the victim mindset and stuff like that. But it's obviously like an endless journey because everyone's going to fall into the same things. But the way you solve is obviously to break down everything into smaller steps, and then you just construct the thing from the fundamentals. And if you don't know, then you have to explore from the higher level concept. You have to create questions that are going to allow you to create a path that breaks down the thing into more simple things you can do. And I think if you do it like that, then ChatGPT becomes very useful because it's just a better search. It's just an easier way to search for things. And then obviously if it doesn't work, you can just use the normal search engine. But I think people are using it wrong probably. What they're probably doing is what I just talked about. They search for something and then it doesn't work, and then they give up and they blame on the thing. It's just human nature. And another thing that I was thinking about is, but I still haven't figured this out, and it might be, not sure if dangerous, but like there must be ways to communicate with ChatGPT. I think it falls in the thing of the jailbreak stuff, but not even in a jailbreak kind of way, more in a, because it relates to the process of communication as well, which is something I've been thinking about a lot as well. Because the way you communicate is going to change everything, and the way human beings communicate is by compressing information we have in our minds and then putting into words, and then because we know the same words, we synchronize with ourselves. And what changes the discussion a lot that people have is the amount of compression that they did in order to encapsulate complex things into concepts that they have roughly the same amount of understanding of what that's supposed to be. So the point is that there's probably a way to communicate with ChatGPT or artificial intelligence in a way that allows you to compress concepts into like structures, and then it becomes more efficient. But I haven't figured out a way to do this or to go about doing this. Because you can imagine, like, instead of putting the text here, I could put some code or some binary structure or something like that, and then you would output what I want in a much better way. And obviously it's gonna have to do with the architecture of the network, I think. But I think this is interesting as well because it also relates to the way that you watch videos. One thing I've been noticing is that the more videos I watch at 2x speed and 3x speed, the easier it becomes to understand. And I think the reason why is because if you think about it, the difference in speed is just like the same differences you have when it comes to two different languages. So when you go faster, it's almost like the person is speaking a different language. And then you can encode information in your brain in a different way that is going to allow you to understand what they're saying without... You're basically changing the meaning of the words by compressing the information. But obviously the downside of that is that there's loss of accuracy. So, because every time, and I think that's the same reason why people have problems communicating with each other. Because when you compress high level concepts, it becomes more likely that the representation you have is going to be different than the representation that the other person have. Because the path for construction to make that concept is going to be different for both of you. I think I'm gonna read this with the text-to-speech. So the reason why I think it's better to study these things is because of trying to break down everything to fundamentals and superficial things. Because if I just build the parser without understanding these things, then maybe it works, but then it's not gonna allow me to break them down, I think, into the lowest common denominator. And probably it's gonna have to do with this. I think the fundamental thing is this thing about grammar. Is the notion of what is the space of possibilities of symbols that can represent a computational sequence. I think this is the fundamental essence of the programming languages. And figuring out the fundamental differences and superficial differences is going to be related to this. So I should probably study this more and understand how it works. But if it's too hard, then I just go back to doing the practical stuff more, and then I go back and forth between them until I have something. I think it's probably the best way.
One, how is grammar related to the compilation and interpretation process of programming languages? What is terminal and non-terminal in the context? Chapter 1. One, grammar and its role in programming languages in the context of programming languages. Grammar refers to the formal rules that dictate the syntax and structure of the language. A programming language grammar defines how statements, expressions, and other language constructs are formed. It specifies the correct order and arrangement of tokens, keywords, identifiers, operators, etc. in a valid program. Programming language grammars are essential for both the compilation and interpretation processes. A grammar defines the rules that a program must follow to be considered syntactically correct. This is crucial for both compilers and interpreters to understand and process the code correctly. Compilation process and the compilation process. The source code is translated into machine code or intermediate code that can be executed by a computer. The compilation process involves several steps. Lexical analysis. This step involves breaking the source code into tokens, such as keywords, identifiers, operators, and literals. Syntax analysis. This step uses the programming language's grammar to check if the tokens form valid statements and expressions. It constructs a parse tree or abstract syntax tree (AST) to represent the hierarchical structure of the program. Semantic analysis. After ensuring correct syntax, the compiler checks the semantics of the program. This includes type checking, scope resolution, and other semantic rules. Intermediate code generation. Some compilers generate an intermediate representation of the program that is easier to optimize and translate into machine code. Code optimization. The compiler performs various optimizations to improve the efficiency and performance of the generated code. Code generation. Finally, the compiler generates the target machine code or executable from the optimized intermediate code. Interpretation process. In the interpretation process, the source code is executed directly by an interpreter without producing a separate compiled output. The interpretation process involves similar steps to compilation. Lexical analysis. Tokenizing the source code. Syntax analysis. Parsing the tokens according to the language grammar to create a parse tree or AST. Semantic analysis. Checking the semantics and executing the program step by step. Terminals and non-terminals. Terminal symbols. These are the basic building blocks of a programming language, such as keywords, identifiers, constants, and operators. Terminal symbols are the tokens recognized by the lexical analyzer. They are the smallest elements in the language's syntax. Non-terminal symbols. These are symbols that represent groups of terminal and or non-terminal symbols. Non-terminals are used in the grammar rules to define the structure of statements, expressions, and other language constructs. Non-terminals are expanded into sequences of terminals and other non-terminal. The interpretation process involves similar steps to compilation. Lexical analysis. Tokenizing the source code. Syntax analysis. Parsing the tokens according to the language grammar to create a parse tree or AST. Semantic analysis. Checking the semantics and executing the program step by step. Terminals and non-terminals. Terminal symbols. These are the basic building blocks of a programming language, such as keywords, identifiers, constants, and operators. Terminal symbols are the tokens recognized by the lexical analyzer. They are the smallest elements in the language's syntax. Non-terminal symbols. These are symbols that represent groups of terminal and or non-terminal symbols. Non-terminals are used in the grammar rules to define the structure of statements, expressions, and other language constructs. Non-terminals are expanded into sequences of terminals and or other non-terminals during parsing. For example, consider a simple grammar rule for an if statement. Rust copy code if underscore statement greater than if condition statement if and are terminal symbols. Condition and statement are non-terminal symbols that represent further expressions or statements. In summary, grammar plays a fundamental role in programming languages by defining the syntactic structure of valid programs. Both compilers and interpreters use the grammar to understand, analyze, and process the source code during compilation or interpretation. Terminal and non-terminal symbols are key concepts within a programming language's grammar that help define its syntax and structure.
The other thing I can do is just study the V8 engine. I think I'm gonna do that. But maybe it's a waste of time. There's a lot of things to do, so. I think I'm gonna download this and put on the. I'm gonna put here. And maybe it's a waste of time, but I'm gonna download this and then I'll think about it later. I'm gonna do the other stuff first. Then maybe I'll come back to this and try to study. Because there's gonna be a bunch of files that doesn't matter for like what I'm trying to understand. And I don't think it's worth trying to rebuild this stuff because it's not the same thing that I want to do.
One, are non-terminal symbols part of the language, or are they broken down into terminals eventually? Chat 1. Non-terminal symbols are not part of the language itself. They are constructs used in the context of the language's formal grammar. Non-terminals represent groups of symbols, including both terminals and other non-terminals, which are further broken down during the parsing process. The goal of non-terminals is to define the hierarchical structure of valid language constructs. In the context of parsing, non-terminals serve as placeholders that help guide the process of constructing the abstract syntax tree, AST, or other intermediate representations. As parsing progresses, non-terminals are expanded into sequences of terminals and or other non-terminals according to the rules defined in the grammar. Let's consider an example using a simplified grammar for arithmetic expressions: bash copy code expression, greater than term plus expression, term dash expression, term, greater than factor slash term, factor, greater than expression. Number in this grammar, expression, term, and factor are non-terminal symbols. Number, plus, slash, and are terminal symbols. When parsing an arithmetic expression like 3 plus 5, 2, the parser would start with the expression non-terminal. Expanded to term plus expression. Expand term 2, factor term. Expand factor 2, expression. Continue expanding the non-terminals and terminals until the entire expression is parsed. At each step, non-terminals guide the parser's decisions on how to expand the syntax of the input. Eventually, non-terminals are broken down into sequences of terminals, leading to the creation of a concrete representation of the expression, such as an abstract syntax tree. In summary, non-terminal symbols are not part of the language itself. They are constructs used in formal grammars to describe the syntax and structure of valid language constructs. During parsing, non-terminals guide the breakdown of input into sequences of terminals and other non-terminals, facilitating the construction of meaningful language structures. When interpreting JavaScript with an engine like V8, which uses just-in-time compilation, there's a complex series of steps that occur before the code is executed as native machine code. Let's break down the process. Lexical analysis and parsing. The JavaScript code is first analyzed to break it into individual tokens, lexical analysis. These tokens are then parsed according to the language's grammar, forming an abstract syntax tree, AST. Abstract syntax. Tree, AST. The AST represents the structure of the JavaScript code in a tree-like format, capturing the relationships between statements and expressions. Intermediate representation. IR. The AST is converted into an intermediate representation, IR, that's more amenable to optimization and further processing. The IR may involve various levels of abstraction, with high-level operations being broken down into more low-level ones. Optimization. Various optimization techniques are applied to the IR, aiming to improve the performance of the code. These optimizations can involve inlining functions, eliminating dead code, reordering instructions, and more. Code generation. The optimized IR is transformed into lower-level intermediate code. This lower-level code is usually closer to the target machine architecture but still not binary machine code. Just-in-time compilation. JIT. The intermediate code is compiled into native machine code just before execution, thanks to the just-in-time JIT compilation. JIT compilation allows the engine to tailor the code generation to the specifics of the current execution environment. Execution. The generated native machine code is executed by the processor. During execution, the engine manages memory, data structures, and control flow as required by the JavaScript code. Memory management and data structures. JavaScript engines like V8 manage memory and data structures to execute JavaScript code efficiently. Stack and heap. JavaScript engines often utilize a combination of stack and heap memory. Stack memory stores function call frames and local variables, while heap memory is used for dynamically allocated objects. Data types. JavaScript engines manage a wide range of data types, including integers, floating point numbers, strings, objects, arrays, and more. Garbage collection. JavaScript engines employ garbage collection algorithms to automatically reclaim memory that is no longer in use, helping prevent memory leaks. Memory allocation. The engine handles memory allocation for objects dynamically created during runtime. Objects can be allocated on the heap, and the engine manages their lifetime and deallocation. Type. Information. Modern engines use techniques like hidden classes or inline caches to optimize property access, improving execution speed by optimizing memory layout and access patterns. Runtime environment. The engine provides a runtime environment that emulates JavaScript's behavior, including function call stacks, execution contexts, scope chains, and more. In conclusion, interpreting JavaScript involves multiple stages, including parsing, abstract syntax tree generation, optimization, intermediate code generation, JIT compilation, and finally, execution. Throughout this process, the engine manages memory, data structures, and the runtime environment to execute the JavaScript code efficiently and in compliance with the language specification.
I'm not sure if this is a good question, but I guess this is what I'm trying to clarify is because the V8 is obviously going to be the thing that parses the code into the binary instructions. But is it like the V8 makes sure that the syntax is valid in relationship to the grammar rules that it has, but what determines if the instructions are valid at the hardware level? So the only thing that I can think is that the operational system is the thing that executes the code because it's the thing that is going to have access to the priorities of the user and is going to determine how the application is going to interface with the hardware. So I guess this is the question that I'm trying to clarify. And I think this is going to be different, obviously, to different programming languages because they're going to relate to the operational system in a different way. But I don't remember. I think on the C compiler, he doesn't. Maybe he talked about this, but I don't remember. But I think he didn't because the course that I did is just the beginning. He has other modules, so he probably didn't talk about that. So I need to find videos that have this explanation of the last step before the code gets executed. Like what is it exactly that is getting the instructions in binary and executing them? Because how do you define that instruction has a meaning? Because obviously the language is going to define the rules, but then like how does the operational system know if the rules make sense or? But I'm not really sure how to ask that because I think that this question I'm gonna ask this question, but maybe it's too generic. Maybe I have to think more about the like how to break this down so I can find the nuances.
At the final step of executing code generated by a JavaScript engine, it's the CPU, central processing unit, that directly executes the native machine code. The operating system plays a crucial role in managing and coordinating various processes, including running applications and managing memory, but it's not directly involved in the actual execution of the code generated by the JavaScript engine. Here's how the process typically works. Generated native machine code. The JavaScript engine generates native machine code that the CPU can execute. This code is a sequence of low-level instructions that the CPU understands. CPU, execution. The CPU fetches these instructions from memory, RAM, and executes them sequentially. It performs arithmetic and logical operations, moves data between registers and memory, and follows the control flow specified by the instructions. Operating system's role. While the operating system doesn't directly execute the code, it provides the environment in which the code runs. It manages memory allocation, process scheduling, and provides system services. The operating system also ensures that different processes, including the JavaScript engine's execution, are isolated from each other and don't interfere. Hardware interaction. The CPU interacts with other hardware components like memory, registers, and peripherals to execute the instructions. The CPU's microarchitecture determines how these operations are performed at the hardware level. In summary, the CPU is responsible for executing the machine code generated by the JavaScript engine. The operating system provides the environment in which the code executes.
The discussions like it clarifies, but they're not exactly what I'm trying to know. Is I have to think more about this. I want to ask something that allows me to understand what is the gap. Because there's the people that create the interpreters and compilers, and they don't necessarily need to know the CPU microarchitecture. And it wouldn't make sense that you have to think about all the architectures possible to create, which makes me think that there's probably a standard. If that's the case, for a CPU architecture, there's gonna have like a series of instructions, but then how does that work? Because you can imagine that the programming languages are going to be there is an infinite amount of potentials that different programming languages you can have, an infinite amount of architectures as well. So how would you make sure that the instructions are always going to be interpreted in the correct way when they get to the final part? Because it seems like the interpreter is one thing and the CPU microarchitecture is another, but they are obviously related. And I think that at the low level is going to be the BIOS, and the BIOS is programmed based on the read-only memory. So you put a set of instructions on the read-only memory that is going to initialize the bootloader, which is the thing that initializes the BIOS. And based on that, there's going to be a bunch of commands on the hardware itself that is going to load the graphics interface for the BIOS. And then from that command, you can create your own operational system, and then you can load your own operational system, which is going to be just code that is going to manage the memory and the hardware, and it's going to create different levels of users that have different priorities, and it's going to create the file system. And then it's going to create processes or commands to determine what's going to happen when different processes are running at the same time and how to manage everything. And also virtual memory and pagination to increase the efficiency of the memory and the virtual file system as well. And then based on that, it's going to determine what runs. But I guess this distinction between the user code and the operational system code is maybe I should go back into the other course, the operational system course, and try to find the part that he explains the thing is that he doesn't, because the course is more general, he doesn't focus specifically on that. So I think like it's not very good to understand. I need to think more about this. So how to find, maybe I should ask this to ChatGPT as well. I think this is the thing that I need to clarify to understand what's the fundamental, what's not. Because I think that's probably the bridge. That's the main distinction. Like obviously there's other distinctions, but this is the fundamental one from which all of the other ones diverge. Because the main difference between them is going to be the main fundamental difference between them is going to be the way that they use memory. And the other one I think is on the way that they shape the abstract syntax tree to generate the code. So I guess another question is why, like how do you think about the process of developing the grammar space, which would be like the terminal syntax, the terminal symbols we're gonna have, and how they're gonna translate into the code. For example, why not? Like, obviously, for this example that I'm going to give is obvious, but for other ones might not be that obvious. So, like, why don't you have two different symbols that represent functions? Actually, in Python, you have lambda and the normal function, the daf. And obviously, the reason why you have them, the two different ones, is because there's going to be a fundamental difference in the way that they are stored in memory, I think. Because lambda is like an anonymous function, and then it's going to change the way that the memory works. So I guess like what I want to clarify is how at what point exactly the instructions change the way that the memory is going to be used. Maybe that's a good question. I think that the main difference in speed is always going to be related to memory because it's just differences in accessing the memory. And I think that the CPU is going to have different threads, which are going to have different caches. And the cache is going to be a structure where it's going to be L1, L2, L3, I think. And then you have RAM and you have the hard disk. Or, yeah, not sure. I think it's hard disk. And that creates the funnel. That's the more, if you want to access things on a hard drive, I think. Hard drive, it's a lot slower, but then you have a lot more space. L1 cache is a lot faster, but less space. And the differences, fundamental difference between languages is going to be the way that they access the memory. I think that's the main one. And that's going to translate in the speed differences, which is going to also the conversion between types as well. At what points the I do think that there's differences in the operation. Differences in the way the operational system works should change the speed of the languages. But like intuitively, that's how I think because it makes sense. But I never seen like anyone talking about it like this, so maybe it doesn't make sense. Because like in one way, it would make sense that is not related because then like obviously you want the programming language to always run the same way regardless of which system is executing. But then in another way is it has to be related because then the operational system is the thing that is going to be connected to the hardware. And then the hardware is going to be the thing that determines how the types are converted between each other. So it has to have something to do. And that's what makes me think that there probably are standards in the same way that there are standards to create the BIOS. Because that's the only way to synchronize. In the same way that you have standards as well to create the strings. So I think there are standards. The true complement system is probably, but the question is, does everyone use the same system to translate? I think that's probably no, the answer. But then the question is, how does the programming language, if it matters, if the programming language, like, does that matter? I think it does matter, but it matters to a certain extent because obviously it's going to run differently depending on the hardware. But then, like for the structure of languages itself, it doesn't matter that much because even though there are going to be differences, it's going to be the same, if that makes sense. It's kind of hard to explain. Like even though like JavaScript code can run faster in one machine than the other one, like the structural essence of the language is what matters, I think, to me. So that difference doesn't matter because the way that it is managing memory is always the same, like the logic behind it. What's going to be different is just on the lower level on the hardware and the operating system on how it converts everything. When on the high level structure is always the same. Like the same logic, the same path to convert. So yeah, this is the thing that I have to clarify is at what point is gonna matter because it's directly related. And then how does that, how did they solve this? If there's a standard or something like that.
One, how does the CPU understand the instructions? Does differences in CPU's microarchitecture change the way it's going to interpret the programming language? Chapter 1. The CPU understands instructions through a combination of its microarchitecture, instruction set architecture, ISA, and control circuitry. Let's break down how this works and address the impact of microarchitecture differences on interpreting programming languages. 1. Instruction set architecture, ISA. An ISA is a set of instructions that a CPU understands and can execute. It defines the vocabulary and syntax of machine instructions, including operations like arithmetic, logical, memory access, and control flow. Each instruction is encoded in a specific format that the CPU can decode and execute. 2. Microarchitecture. The microarchitecture is the physical implementation of the CPU's functional units, pipelines, registers, cache hierarchy, and more. Microarchitecture decisions affect the performance, power efficiency, and overall behavior of the CPU. How? The CPU understands instructions when the CPU executes machine code instructions. It goes through a sequence of steps. Fetch. The CPU fetches the next instruction from memory. The memory address is determined by the program counter, PC. Decode. The fetched instruction is decoded to determine its operation and operands. This is where the CPU understands what the instruction is asking it to do. Execute. The CPU executes the instruction by performing the appropriate operations, such as arithmetic, logical, or memory accesses. Write back. If necessary, the result of the execution is written back to registers or memory. Impact of microarchitecture on programming languages. Differences in CPU microarchitecture can indeed impact the interpretation of programming languages. Here's how performance. Different microarchitectures have varying levels of performance due to differences in pipeline depth, cache size, branch prediction strategies, and more. This affects how quickly code is executed, potentially making certain language constructs more efficient on one microarchitecture compared to another. Optimizations. Modern CPUs often have features like out-of-order execution and SIMD, single instruction, multiple data units. Compilers and interpreters can leverage these features to optimize code execution. However, the effectiveness of these optimizations can depend on the CPU's specific microarchitecture. Instruction set extensions. Some CPUs support specialized instructions, called extensions, that can accelerate certain operations. For example, CPUs with SIMD extensions can perform parallel operations on multiple data elements. This can affect how certain language constructs are executed. Resource management. Microarchitectures have varying sizes of registers, cache, and execution units. How efficiently these resources are utilized can influence how code is executed and how the runtime environment, for example, garbage collection, memory management, behaves. Latency and throughput. The latency and throughput characteristics of various instructions and memory operations can impact the responsiveness and overall performance of interpreted code. In conclusion, CPU microarchitecture can influence how code is interpreted and executed. While programming languages are designed to be portable across different architectures, fine-tuning code for specific microarchitectures can lead to better performance in some cases. Optimizations may need to be tailored based on the target architecture to fully leverage its capabilities.
This part here is the one that I was confused about, but then after watching the Ben Eater series several times, I think I understand this very clear now. Very clear. I'm not sure if that's how we put it, but it just fetches from the counter and then puts in memory and then goes to the ALU, and then based on the ALU, there's carries and different registers that are going to determine what's the next instruction is going to be. And then based on the calculations, you can have the jump conditional instructions or conditional instructions. If it's 0, you do something. If it's not, you do something else. So I think I understand that very well now. But I have to think more about like a good question to clarify, because I do think that this is correct, and I think it does make a difference because it makes sense. So I also think, like, I remember studying a while back something that they created through arbitrage, which is simulated bifurcation machine, which is a machine that they created just based on quantum mechanics, and I forgot the name of the thing. There was a name of the thing that they did. It's pretty much based on the states of the binaries. It's pretty much a hardware that is designed to do that kind of computation faster. And obviously, I think that it is connected. So the structure of the hardware is going to determine how the instructions become managed memory, obviously. So the question is, where is the boundary of when the language becomes is like when the language is going to be the same everywhere? So you can imagine, like, at the very top, when you have the lexer, is always going to be the same regardless of the hardware, because it's just the structure of the language itself. And then at some point, it becomes dependent on the hardware. So it's like a funnel of information. And the question is, at what exact point does that happen? And then how is going to translate in the differences between languages? Lagrange mechanics. Yeah. I'm not really sure if it's Lagrange. Something like that. Maybe I still have here somewhere. Simulated bifurcation. I forgot the name of the thing. Ising model. Yeah, that's the name. I'm not sure if it works, but I studied some stuff about this before, and they pretty much created a machine that is optimized for this. But there's other name that I forgot that is related to the Ising model. Whatever. So let me think about that. I think I'm gonna ask this question. I'm gonna spend like probably 20 minutes, something like that, and then I will stop streaming, and then I'm gonna go watch the course again, and go back from the beginning. I'll be right back. I think I know a good way to figure out. I'm gonna ask first at what point. No, does the Lexer and abstract base structure language? No, let me think. I want to ask in a way that is going to tell me whether or not it is different than is different based on the hardware or OS. Then based on this, I'm going to go back and watch get this process here. I'm gonna write down, and then based on the process that it told me that it goes through, I can ask like at what point of this process. Yeah, I think this is this one. when I ask at what point does the hardware starts to interfere, then once I figure that out, then I'm gonna watch videos about that. But I think the first thing that I'm gonna do off stream is just watch the course again, and then I'm gonna see like what is the point of that make file and what kind of things he uses to run the code and to debug the code. I think I need to learn that first. Once I learn that, already it's not that hard to parse the file, so I'm just gonna break down the code that he has there, I think, and then copy some of the code and then try to do it. Like, I'm not gonna write down everything from scratch because I think that doesn't make sense. I think I'm just gonna copy a lot of stuff he did, and then I'm gonna change the stuff that he did in order to do something that I want to do, like something that is more simple. And then I go from that point. But I'm also gonna study this stuff here as well.
One, does the lexer and abstract syntax tree structure of a language is different based on the hardware or operational system? Fact 1. The lexer and abstract syntax tree AST structures of a programming language are primarily influenced by the language specification, rather than the hardware or operating system. However, there can be some subtle differences or considerations based on the target hardware or operating system lexer. The lexer's main task is to break down the source code into tokens, keywords, identifiers, operators, etc. The structure of the lexer is generally determined by the language's grammar and syntax rules, which are defined in the language specification, while the lexer itself is not directly affected by hardware of a language is different based on the hardware or operational system? Fact 1. The lexer and abstract syntax tree AST structures of a programming language are primarily influenced by the language specification, rather than the hardware or operating system. However, there can be some subtle differences or considerations based on the target hardware or operating system lexer. The lexer's main task is to break down the source code into tokens, keywords, identifiers, operators, etc. The structure of the lexer is generally determined by the language's grammar and syntax rules, which are defined in the language specification, while the lexer itself is not directly affected by hardware or operating systems. There might be some minor considerations character encoding. Different systems might use different character encodings, which can impact how characters are read and tokenized by the lexer. However, this is usually handled at a lower level in the language processing pipeline. Abstract syntax tree AST. The AST represents the hierarchical structure of the program according to the language's syntax. Like the lexer, the AST structure is mainly driven by the language's grammar rules. However, there are a few points to consider. Memory layout. The representation of the AST in memory might differ based on factors like the alignment requirements of the target hardware architecture. This is usually an optimization consideration, and modern compilers and interpreters handle it transparently. Optimizations. Depending on the target hardware and system capabilities, the AST might be optimized differently during compilation or interpretation. For example, certain optimizations might be more effective on systems with extensive vector processing capabilities. System-specific behavior. If the language specification allows for system-specific behavior, for example, system calls, platform-dependent code, the AST might reflect this through conditional nodes or other constructs. Operating system interfaces. If the language interacts with operating system APIs, for example, file I/O, networking, the AST might include nodes representing these interactions. However, this is more related to the semantics of the language rather than the hardware. In general, while hardware and operating systems can influence certain aspects of language processing, for example, memory layout, optimizations, the lexer and AST structures are primarily shaped by the language's specification and grammar. The goal of language designers is to ensure that these structures remain consistent across different platforms to provide a portable programming experience.
Trying to think if I can ask something because I want to know like what is the exact representation in binary, because based on the Ben Eater series, the way that he did it, he builds from the ground up, and that's the difference. Like here, I'm going from top down. So in the way he does it, he encodes the instruction based on the read-only memory, and then that means like you put whatever binary configuration you want to represent that instruction. So you create like binary impulses that are gonna represent that instruction, which are based on the EEPROM logic, which is the combinatorial logic. So the combinatorial logic holds the state that is gonna be synced with the flags that of the control logic of the computer that are gonna determine what's gonna happen when that combinatorial logic fires or goes to the bus. So what I wanna, so in the other way, what I wanna understand is like at what exact point does the syntax become the, how does the computer know what the binary instruction from the language means? Is there a standard for the binary itself to mean something? Like how, what is this step that translate the last step that translates the high level instruction into the binary itself? Because the binary has to mean something for any CPU architecture, I think. So what is that essence of the thing? Does is it based on the EEPROM, and is the person that is creating the compiler responsible for knowing that or for setting that up? Maybe like it doesn't necessarily mean that they are responsible, because obviously nowadays you're gonna have other programs that run the code. So if you're building the thing in C, this thing that runs the C code already has a logic built into it. But I want to understand like what is the, at what point does it matter? Is the difference there? I think I'm gonna ask this, then I'll think about it. 'Cause I can like say the stuff about the EEPROM first and the read-only memory, and then ask another question based on that. Maybe that will be better.
The operating system and hardware are involved in managing the execution of code at different points in the compilation and interpretation processes, but they primarily come into play during the final stages of execution, after the code has been transformed into machine code. Here's how the involvement of the operating system and hardware corresponds to the steps you mentioned. Compilation process, lexical analysis, primarily language specific and handled by the compiler. Syntax analysis, primarily language specific and handled by the compiler. Semantic analysis, primarily language specific and handled by the compiler. Intermediate code generation, still within the compiler's domain, with language specific optimizations. Code optimization, compiler driven optimization, not directly OS/hardware dependent. Code generation, the compiler generates target machine code that the hardware can execute. At the code generation step, the compiler produces machine code that follows the target hardware's instruction set architecture, ISA. The operating system doesn't yet play a significant role in this process. Interpretation process, lexical analysis, primarily language specific and handled by the interpreter. Syntax analysis, primarily language specific and handled by the interpreter. Semantic analysis, primarily language specific and handled by the interpreter. During interpretation, the interpreter translates high-level language constructs into lower-level operations. At this point, the operating system and hardware start to become more involved. Operational system, the operating system manages the execution of the interpreter process. It allocates resources, schedules execution, and provides an environment for the interpreter to run. Hardware, the CPU executes the machine instructions generated by the interpreter. The hardware follows the instruction semantics based on its ISA. Understanding binary instructions, the operating system doesn't directly understand the semantics of binary instructions for a specific programming language. Instead, the operating system and hardware operate at a lower level, dealing with machine instructions that are expressed in a specific instruction set architecture, ISA. The relationship between the high-level programming language, its compiler/interpreter, and the hardware's ISA is mediated by the compiler/interpreter. The compiler translates high-level language constructs into machine instructions that the hardware understands. The hardware's microarchitecture is designed to execute these instructions efficiently. In essence, the operating system and hardware are responsible for executing machine code, but they don't interpret the programming language directly. The compiler/interpreter bridges the gap by translating language constructs into machine code instructions that the hardware can execute.
I think this is the key. Is this, and I know that he said something about this, but I wasn't paying attention. I was paying attention to the other stuff. But looks like this is the point. So I need to understand this hardware's instruction set architecture. And I think this is the thing that I want to clarify. Like, I think it's gonna be neither. The response is gonna be somewhere along the middle, but I think that's the distinction. So, like, do you develop a hardware that has this ISA, whatever you say that, instruction set, that is gonna handle any programming language, and then regardless of how you code the compilation process of the programming language, the ISA is gonna figure out what the code means, or is the responsibility for the programming language to create a binary in such a way that any ISA is going to understand, because you can imagine that there's going to be an infinite there can be an infinite amount of different instruction set architectures and an infinite amount of programming languages. So the answer is probably going to be a convergence between them in the middle, because it's a polarity, relativistic polarity that encapsulates a paradox that is going to have a singularity that is going to have infinite potential, and the evolution of the relationship between them is going to be the flow of information of space-time. So depending on the complexity of the environment, which is subjective, is going to shape the structure of the relationship between this and the programming language. And I think that this is probably one of the key distinctions to, and being able to create that tree that highlights the fundamental differences between programming languages and the superficial differences, because it's related to how it's going to handle the memory at the hardware level. So I think I'm gonna read this and then I'm gonna stop. I'm gonna read this with text-to-speech, then I'm gonna go do the course again off stream.
The responsibility for allowing the instruction set architecture, ISA, to understand code from a programming language primarily lies with the compiler or interpreter associated with that language. Let's clarify how this process works. 1. Compiler/interpreter responsibility. The compiler, for compiled languages, or interpreter, for interpreted languages, is responsible for translating the high-level constructs of a programming language into the machine code instructions of a specific ISA. This translation is tailored to the target hardware's ISA. Compilation. For compiled languages, the compiler generates machine code during the compilation process. The generated machine code adheres to the ISA of the target hardware. Interpretation. For interpreted languages, the interpreter translates high-level constructs into lower-level operations that can be executed directly by the hardware. 2. ISA design and compatibility. Hardware's ISAs are designed with specific features and instructions that enable efficient execution of a wide range of programs, but they are not inherently designed to understand any possible programming language instructions. Standardized instructions. ISAs have standardized instructions for common operations, such as arithmetic, memory access, and control flow. These instructions are designed to be versatile and applicable to various programming languages. Compatibility. While ISAs are not designed to understand any programming language, they are designed to be compatible with compilers and interpreters that generate machine code according to the ISA specification. 3. Language compatibility. Programming languages are not developed to automatically translate instructions for any possible ISA. Instead, language designers focus on creating a syntax and semantics that are human readable and easy to use. They rely on compilers and interpreters to handle the translation to machine code that the hardware can execute. In summary, the compiler, or interpreter, is responsible for translating high-level programming language constructs into machine code instructions of a specific ISA. The hardware's ISA is designed to efficiently execute a wide range of programs and is compatible with compilers and interpreters that generate code adhering to its specification. Programming languages are not designed to translate instructions for any ISA. That task is handled by compilers and interpreters. In essence, the relationship between programming languages, compilers/interpreters, and hardware ISAs is a coordinated effort. Language designers create languages that are human readable and expressive. Compilers/interpreters bridge the gap to generate machine code, and hardware ISAs provide the framework for executing that machine code efficiently.
So it's like I said, is a standard, and standards are synchronicity on the network, I think. So, yeah, and I think it's very similar to like cryptography, but obviously different, but similar in the same way that the standards are going to create a synchronization mechanism between the network. So whenever you're going to have these differences, there's going to be a standard, and there's going to be problems with the standard because it's not going to be flexible enough, and it's going to depend. So it's going to be like both good and bad at the same time, because I think it approaches the boundary of the paradox, because what defines the standard is going to be the relativistic relationship of the nodes of the network that creates the geometrical structure of spacetime. So the standard is the gravitational force between the different reference frames, and I think it has infinite. It doesn't have infinite complexity. It converges towards infinite complexity, because that's the funnel of information. So I'm gonna stop here, and I'm gonna do that stuff. I'm not sure when I'm gonna stream next time, but I'm gonna continue to do this stuff here. And I think I'm gonna take more time now to, and for the build space stuff, I don't think I'm gonna do, like, if I can't do anything that's gonna be useful, I'm just gonna do a video, a small update based on the stuff that I already have right now, and then I'm gonna continue to build the way that I'm building now, because I think that it's better to solve this first. I'm gonna try to go back and forth, but I need to study the course first, and there's so many things to learn. So I'm probably not going to be able to have something that is going to be useful until Monday unless I neglect this stuff and I focus more on creating something which I think it doesn't make sense. Like creating something like just to parse files. For example, like in a simple way here to show something. I think that it doesn't make a lot of sense to me. It makes more sense to spend time figuring out this now. But hopefully next week I'm already gonna be able to build something useful. Because now I think that for the most part, uh, except the couple of things that I have to fix here, which is this broken thing here that I have to see, and the arrows here, like some small things. I think that this part I'm not gonna focus that much anymore. It's gonna be more on the other parts, so I'm gonna have a lot more time to figure that out, other stuff out, and then obviously once I figure that out, and I'm gonna go back and forth forever, because there's like billions of things that I can do still.